Our last topic in this unit of integral applications is called arc length. It is a BC-only topic, and you might remember studying arc length back in geometry when you found the length of an arc of a circle. And we use calculus to find the length of not just arcs on circles, but on any curved function that we would like. And it does have a geometry connection in that we are going to be looking at the Pythagorean theorem. So before we get ahead of ourselves, our learning target is to apply integrals to find the length of a curve. So you'll see on my notes, I have a green sample curve, just a hypothetical portion of a function. And I've placed a right triangle on that curve so that the hypotenuse is going to estimate the length of the green curve. So our legs of the triangle are dx and dy for horizontal and vertical, and ds is the length of the hypotenuse. And so Pythagorean tells us the relationship is ds squared is equal to dx squared plus dy squared. So we will now solve this equation for s. So starting with a couple algebraic steps, I will square root both sides of the equation. The second step is a little less obvious. I'm actually going to factor out dx squared as a GCF. When I factor it out of itself, I get 1, and when I factor it out of dy squared, I get dy over dx squared. You'll notice I put the dx squared in the back as a GCF instead of the front like we normally do. Two reasons for that. One, I knew that I could square root dx squared and the dx would come out of the square root. And secondly, in my next step, I would finally like to use some calculus, and that is to take the integral of both sides, which will give me dx as my variable of integration for that integral. So finally, we have our formula for arc length, and we use an integral because it finds the sum of an infinite number of those approximations of ds, adds them all up, and it gives us our exact arc length. You'll notice that our arc length formula can be used in two slightly different variations. A lot like when we studied area and volume, we could write a dx or dy integral and deciding which better fit the situation or the function that we're working with. So I'd like to show you an example of each to show you how each of these works a little bit differently. In our first example, we're going to be doing a dx integral, so our limits need to be x values. We're looking at the square root function between 0 and 1. So we've got our limits, we've got our square root and our integral of 1 plus dy dx squared. So our only job really is to figure out the derivative of this y equals x to the half, substitute it here, and then we'll use our Math 9 to figure out the answer. So we find the derivative is dy dx is 1/2 x to the negative 1/2. Put that into our formula where the dy dx is. And our Math 9 should give us 1.479. So just double check on your end that you can get the same answer. So that 1.479 is the length of the square root function between the intervals 0 and 1. Let's look at another example in which we're going to use the formula in terms of a dy integral instead of a dx. So we're going to be looking at x equals y squared on the y interval 0 to 1. So we'll set up our formula and we'll talk about this derivative that's a little different, the dx dy. So we've got our limits 0 to 1 of the square root of 1 plus dx dy squared. So our only job is to figure out what is this dx dy. So literally it means the derivative of x with respect to y. So I will take the derivative of this with respect to y. That will be 2y. And if you're asking yourself, well, what about the chain rule? Well, what we have here is the derivative of y, which would be dy with respect to y. So dy over dy just gives us 1. So long story short, our term that we need in here is the 2y. When you put your integral into Math 9, you should notice something very interesting. We get the same answer that we did for our first example because Miss Henry did something really clever. I took the same graph and we just found the length both using the x and the y integrals. So there's a reason that's the same answer. Before we meet in class again, I'd like you to try this next example on your own. You're going to need to solve for y and find dy dx, and then take your dy dx, put it into your integral with limits from negative 1 to 1. And I think that you'll find this answer is pretty clever too, based on the fact that we know this is a circle that we're looking at. So see if you can figure out what's going on, and we'll talk about it in class together.